Welcome everyone to the online tutorial. So today we will have the quiz and we'll do some practice together and I'll also explain. And I already upload the quiz to the online modules in Canvas, so we can download it. You can also have a look here. Now let's start. Someone asks, the question is this marked? No. The quiz has no point. So, like I introduced in week 1. Sorry, can you guys see my screen?
Yes.
Okay. Yeah, the quiz is just for practice. It's not related to any assessment. Like there's no point for the quiz. Yeah. Your points are from the 2 assignment and 1 project and the final exam. The quiz is not marked. It's just for practice. Okay, let's start. So the first one, so for this given graph, find shortest path from A to H, and also what is the diameter of the graph. Show one shortest path whose length equals to the diameter. I will give you guys like probably 3 minutes to you can have a try yourself first, and then we will walk through it together. Yeah, we will talk about this question later. Ziyuan, you can recall like the definition of diameter. I think you can find the answer to your question. Okay, so to solve this question, let's review some of the parts we introduced in the lecture. So one is shortest path. So the shortest path is just between the two nodes, the path with the smallest length, right? It may not be unique. So also the question mentioned about the graph, the diameter of the graph. So the definition is the longest shortest path in the graph. That is like all the possible shortest paths in the graph among any two pair of nodes, the longest one. Then we come to the problems. So the first problem is find the shortest path from A to H. Remember we can use BFS to find the shortest path. So if we start from A, the first step we goes to E, F, B is 1. We distance 1, we can reach these neighbors, and then we go to neighbor's neighbor. So from B to C, distance 2, we can go here. B to G, distance 2. F to C, here. F to J, distance 2, E to J. And then we start from neighbor's neighbor. We go from C to G, this distance 3, we can reach D. C to K, distance 3. And from G, we can go to H, distance 3. And from J, we can go to K, distance 3. So the shortest path from A to H, the length is 3, but you can go actually you can go back from H to any, like H, G, B, A. So this is shortest path from A to H with distance of 3. Okay. The next question is, what is the diameter of this graph? So remember the diameter, we need to find the longest shortest path. So yeah, of course, we don't need to list like these pairs like CJ. They can reach in hop 2, like only distance is 2. It's very small. So we will try to find the long away, like far away nodes. For example, like from A, we already find like the distance, the largest distance is 3. And for example, we go from E, we can do a BFX here, distance 1. And then distance 2, A to B, 2. J can go to K2. We can, from 2, we can go to 3. From F, we can go to F to C, F to J. From K, we can also go to C3, also H3. And from 3, we can go to 4, like 4, also 4. So 4 is larger than 3, then we have 4. So you can keep continuing listing all the shortest paths until you have the largest number. So in this case, the diameter is 4. So for the third question, show one shortest path whose length equals to the diameter. So you can just use any, like from the distance between D and E are 4, so you can just go from D and go back to E, 3 to 2 to 1. And it's E, A, B, C, D. This is 1. So this pass the length equals to diameter. Is your answers are the same? Any questions? If not, let's continue to the next question. So the question is, we have a graph whose vertices are all the people in Sydney, and there is the age in if two people were born in neighboring years. Let's say, like one person is born in 1993, that person is born in 1994, then there will be an age between these two persons. If anyone is born in 1995, then there will be from 94 to 91, but there's no age from 93 to 95. So the question is, if we build a graph of all the people in Sydney according to their born years, is this graph connected? I'll give you, say, just 1 minute for you to have a think. Okay. Actually, anyone would like to explain your answer? Any volunteer? Yeah, the answer is connected. Yeah, that's correct. So let's answer this question first. So we review this part about connectivity. So we say a graph is connected if any two nodes are connected. That means there's a path um, between these two nodes. For example, like we introduced here in this graph is a connected graph. If we remove edges, they become two connected components. If we continue deleting, they become four connected components. So in this question, if we draw the graph of all the people in Sydney, and if we draw age between the people, or let's say like people born in 1993, or like all these people. And for people born in 1994, I'll be like this. And then if we draw a graph, there'll be an age from people born in 93 to 94. And then for the other person, it's the same. Also, okay, this continues to 95 until like 2024, the newborn babies. So if we draw this graph, the graph will be like this. Yes, of course it is connected because we can definitely find a path between any two people, like either people from born in like 1990 to the newborn babies. There will be a path from this year, until 2024. So the graph is connected. Yeah. So you asked a question about can it be a giant component? Yeah. What do you think? It is a giant component? Yeah. According to the definition, actually the whole graph is just a component because it's connected. Okay. Interesting question. Thank you. Okay. Now let's think about this question. We have graph vertex. Are the people in Sydney the same? Difference is like if there will be an age if only if two people were born in the same year. This graph connected. We have 30 seconds to think about it. Oh, oops, I already gave the answer here. Yeah, it is no. I think you guys have the same answer, right? Because if we say like same, if we do the same thing, the people born in 1993, if we give an age between the people only born in the same year, then the people in the same year, like these people will be like connected graph. But for all the people in Sydney, they are not, the whole graph is not a connected graph. I think it's quite simple, right? But I just stop drawing. If no question, let's go to the question 4. So, okay, find the strongly connected components of the in the graph. Okay, so this question I'll give you 3 minutes to think about it. Okay. Thanks for all your comments in the chat box. I already see some of you have already put in your answer. Okay. So let's review the part about the SCC. So like we said, SCC inside ICC, each pair of nodes, they must can reach each other. And also the SCC should be maximal. That means you can't add any more node or vertex in the SCC still maintain the property. So to find the strongly connected components of the bar graph, um, like we said, like we introduced, one way is to find the out set of a vertex and inside of a vertex intersect, and then we can have the SCC that this vertex belongs to. For example, let's say we want to find vertex A, the SCC vertex A belongs to. We can find the out neighbors of A. Let's see, out A. We have A can go to E. That's it, I guess. In A, oh, of course, also A itself. In A, this doesn't look good. So in A, we can find like B can go to A. So A, so B, and who can go to B? G can go to B. We have G, then B can also go to A. Then also C can go to G, H can go to G. We have C, H. Then K can go to H. We have K here also. Actually, we don't need to list all these. I think a simple way we just to check if, because we need to intersect outside A and inside A. So it must be a subset of this. We just check if E can go to A. If we check, we can't find any path like E can go to A. So the SCCA belongs to is just A itself. So one SCC in this graph is A. Okay. Now we consider B. So the out B, we just use out OB. Out B has, B can of course go to B itself. B can go, so we already find A itself is a SCC, so we don't need to consider A again. And B can go to B, and also B can go to C and F. C, F, and F can go to E. F can go to J, and B can go to C can go to J, C can go to D. C can also go to K. So the outset, also K can go to H. I think these parts are all the same vertices. And if we now we have outside of B, now we consider in B. So for in B, we have, sorry, for B, the one integer is G. G can go to B. So also B and G. Now who can go to B? C can go to B. H can go to G. Sorry, go to G. So we have C and H. Then who can go to C? B can go to C. B is already here. And we consider H. H, K can go to H. We have K here. And that's it. Then we consider K. J can go to K. And also F can go to J. I think that's all. And then if we do the intersection of these two sets, we can have the SCC that B belongs to is B, C, D here, D is in one set, B, E also in one set, F, we have F, G in both sets, B, C, F, J, and H, yeah, H, J, and last one is K. So this is the SCC that B belongs to. So the second SCC we find, I think, contains most of the vertices, just this part, B, yeah, this part, not D. And the two left vertices, E and D. So they themselves will have a SCC D and E. So in this way, you can find all the SCCs in the graph. The answers are here. Actually, I will share another simple way to find the SCC. So according to the definition of SCC, inside SCC, each node can reach and other nodes. So we can just find cycles here. Because in a cycle, each vertex inside this cycle can reach each other. For example, you have B to C, C to G, G to B. Then these three nodes, they can definitely reach each other, right? And then we can continue to find cycles, like another cycle is probably from B to F, F to J, to K, to H, to J. This is another cycle. So they can also reach each other. But these two cycles, they overlap on B, so that means like all these nodes, they can reach each other. So this is one simple way you can find SCC. Yeah, if you don't understand this, you can just use the intersection of the outset and also the inset. It also works. Is there any questions about this question, this problem? Now let's go to the next question. Are the following two graphs isomorphic? So this question, I'll give you 2 minutes for you to think about it. Okay. So are these two graphs isomorphic? What's your answer? Is anyone who likes to share what your answer and maybe like how you work it out? Yeah, yeah. The answer from Ziyuan is correct. Thanks for sharing. Yeah, and now I will explain it. So firstly, let's review the definition of graph isomorphism. So isomorphism of two graphs G and H is a bijection. So if you can find this bijection between two graphs, between both the nodes and also the edges, then you can say these two graphs are isomorphic. Like we introduced in the lecture, G and H1, they are isomorphic, but G and H2, they are not isomorphic. So when it comes to this question, are these two graphs isomorphic? Yeah, so there's definitely not just one bijection. So you can, as long as you can find a one-to-one correspondence relationship between these nodes and edges, then you can say it is isomorphic. Like one way to map the nodes is we can map node E to H, and we find like the degree of them are both 2, and H connects to J and I, E connects to B and D, so we can map like B to J and D to I. Then B is connected to ADC, ADC. So we can map A to G, C to F. then we can check all the edges if they are mapped. For example, HI, this edge, the corresponding edges are E and D. There's edge here, and then E to J, E to B, and similar for other like BD and JI for other edges. So yeah, from the view, from the layout of the graph, actually, it's also easy to see. Like if you turn this graph like anti-clockwise, and then H stays here, they will be the same. So the answer is yes, those two graphs are isomorphic. Okay, now let's go to next question. You six, what about these two graphs? Can we have check? Another 2 minutes for you. Okay. So yeah, has anyone found like a bijection between these two graphs? Yeah, no. Yeah, it is impossible to find a, so they are not isomorphic. One simple way is like to check. I don't know if some of you are solving this problem in this way. If two graphs are isomorphic, that means like all their nodes are mapped, then the edges are also mapped. That means like the mapped edges, the mapped nodes, they should have the same degree. So one simple way is just to check the degree of the nodes. So on the left, we can say A has degree of 3, B has 1, 2, 3, 4, E has 2, D has 4 degree, C has 3. But on the right graph, we can see F has 3, G 3, H3, I is 4, J is 3. We can see like this graph has a vertex of degree 2. It has 2 edges, but in this graph, there's no node that has degree of 2 or has 2 degrees that can be mapped to E. Something happened to my monitor. Let's just spin. Yeah, okay. So yeah, so that's a simple way to check if two graphs are not isomorphic. You can if the degrees are the same, then you need to like literally to find a bijection to them. Then you can decide if they are isomorphic or not. um, that's all the practice for today. Because for the later questions, we haven't like introduced them in the lecture yet. Next week we will introduce them, and then we will continue the quiz. Do you guys have any other questions? Okay, no problem, no worries. Um, so if no questions, if you guys are interested in finding your teammates here, you can use the time and the chance to meet others and also like discussion, um, or you can just go to any offline labs or tutorials to meet in person. Probably it's easier for you guys. Up to you. But I will still leave the meeting open so that you guys can have the meeting to chat.